Hey everybody, I'm John. Been a part of Techloma for a long time, and so I'm really excited today to talk to you about Web3, this thing that you've probably heard a lot of things about. And I've been building in Web3 with a company that Ryan and I and another partner started called Startup Dev. We're trying to build the bridge between Web2 and Web3. And so I'm excited to talk to you about it today. So I think we've all seen a lot of things regarding crypto and Web3. And I want to kind of take a step back from that, and let's kind of approach this from the technology, and let's kind of see what's happening here, and then we can start to layer on these value judgments or these evaluations. So what we're going to talk about today: why should you care about blockchains? If a server in a database is better or just as good, we don't need blockchains. So we have to have a reason to care about them. How do they work? These are a little bit different than your standard technologies we work with, so we need to understand how they work to understand what useful properties they have. We're also going to look at what the tech stack looks like. What are the valid criticisms? Web3 is not perfect. Blockchain is not perfect. And then what's it like to be a developer in Web3? So my goal for today is to teach you from the ground up. If you have no blockchain knowledge, I hope to completely explain the system to you in a short amount of time, and then familiarize you with the big domain concepts, so when you see these things online, when you Google later, you have a frame of reference to understand what's going on. And then we'll also look at an example dApp. So the two big questions: is this technology useful, and will it succeed? If you get a no to either of those questions, then blockchain is not useful. So first question: why should you care about blockchains? What does decentralization mean? Why does it matter? Let's first look at centralized ledgers. So we use these all the time. These are our banks. This is our legal system. A central party or a small group of parties has all the power in the system. If somebody steals my credit card, I talk to the bank, they control the ledger, they can revert it, no big deal. If I don't pay my mortgage, people take actions to make me pay my mortgage or do things against me with physical force if they need to. So there's some trust here because we trust these parties. You know, we trust that we're talking to the real Amazon.com because of its certificate authorities. And so there are good things about this system, but there are also downsides. And my goal here is not to be political, but there's a group of people who are starting to distrust people with majority power, governments, these systems, the financial systems we work in. And so they say, maybe we should wrestle a little bit of that power back. Maybe there's some different systems we could use that would maybe have better properties than some of the ones we have today. So to understand why a decentralized ledger is useful, let's first kind of do like a little example of how these things work. So I had this really great example in my head when I was thinking about the talk of like, oh, we'll build this ledger that we're all going to use, and it'll be great. I'll show everything. And then I found this video from a channel called 3 Blue 1 Brown, which is fantastic, like math engineering channel. Would highly recommend it. And they did a video on this that's just great. It's got all these nice animations, all these nice graphics, and they basically walk through like how would you build Bitcoin from the ground up. So would highly recommend you watch that. So I'm going to borrow religiously from that video. So let's say we wanted our own decentralized ledger, something we could all use, we could all transact with. We don't trust the banks, we don't trust Venmo. We want our own thing. So we might just put in this ledger what happens. But you might find quickly that some people get tired of paying people money, and so they're just like, hey, this person owes me a lot of money. That obviously doesn't work. We need some authority to prove that you actually authorize this transaction. So the way we do that in a blockchain is we use a digital signature. And a digital signature is made by every person having a public and a private key. And if you're not familiar with cryptographic hash functions, they have these nice properties where I can sign a message verifying that I signed it with my secret key without telling you what my secret key was. It's very easy for you to verify that it's correct. It's almost impossible for you to derive my secret key. So it has this very nice property of being able to easily sign and verify things, but you can't get my secret key, and even if you got one, that doesn't give you the rest of the system. So in our ledger, we can add a signature to each of these lines. Very easy to tell now if these are bogus transactions because the signature will not match for my public key. Next problem you run into, What if we just paste that transaction several times? It's a valid signature, so it works. So what we end up adding is a nonce, or basically the count of transactions for that person to make every line unique. So a little bit down the road, now we have these balances. We need to keep track of them. People need to put money in this system. And you never really have to leave the system as long as you keep kind of just transacting in it. You never have to really pull cash out. If you buy my food, and then later I fill up your gas, and then later you go pick up a thing from Walmart for me, it kind of just evens out in the mix. And so instead of dollars, you might even call these ledger dollars, or tokens, or coins. So where's this ledger that we're all writing on? If we want it to be decentralized, we all need a copy of it. And then you would tell me, hey, I sent this person some money. And so you want to send somebody some ledger dollars, you're going to broadcast that to everybody. Say, I gave Aaron 50 ledger dollars. But if we're all doing this and there's this flurry of transactions happening, the chance that all of our ledgers look the same is pretty unlikely, especially as the system grows. So how do we know what's going on? It matters if I pay my rent and then buy gas and then send you money versus you send me money, gas, rent. Like, the order matters here. So in the Bitcoin system, they added this system we've probably heard of called proof of work. So there's essentially a race between all the components to solve a math puzzle. For example, finding a value that when hashed starts with 30 zeros. And the first person to find this value becomes the leader and is able to write the transactions to the ledger. And so whoever wins this becomes the block producer. And then the previous value is linked to the next block. So that way, every time it's new, you don't get to reuse your value because the initial state has changed. So you're building this chain of blocks. That's the blockchain. And that's how the ledger is built out over time. So we have some core concepts here. We have a transaction, we have the signature, and then we have the block, and then those are changed together. Okay, why would anyone want to do this? If you're done using the system, if you've never wanted to use the system, why would you do this? Now, I know no one here has ever, say, downloaded a movie or a game or a song, but if you did this, someone that we know did this, you know that this is pretty unreliable. Go try and find like Age of Empires peer-to-peer download. It's probably not out there, and you're probably going to get malware. So we need an incentive for people to continue to upkeep and use this system. And a powerful incentive is money. So the producer of the block gets a reward in the currency of that system. So that's kind of like the speed run of how Bitcoin works. Is this useful? So let's look at some of these unique properties of a blockchain. We say this word decentralization, but what does this mean? It means that for every node participating in the system, it adds strength to it. So if Apple gets a subpoena for some information, they're legally obligated to provide that information. There's like, boom, one-stop shop. Maybe this is spread across servers, maybe it's spread across databases, but it's pretty easy to turn these levers on and off. In a decentralized system, even if you compromised a node or some large number of nodes, if you have thousands or millions of miners, the integrity of the system does not falter. The second property that people often talk about is a blockchain being permissionless. And so that means to work in this system, all you need is an internet connection. Because with a couple lines of code, you have a private key. If you have a little bit of the currency to transact, you can now use this system. Doesn't matter what country you're in. Doesn't matter, if you've put in your birth date or your social or your date of birth or your address, any of this KYC information. If you have an internet connection and a mobile device, you can participate in the system. Again, not to get political, but we saw this happen when donations were happening for the Ukraine and Russia war. It was very easy to be like, here's our address. And now anybody in the world in seconds can send money to those causes. The final thing that you get is you get digital ownership. So if you have, let's say, a playlist on Spotify, or you've bought a movie from Apple, they have ultimate control to make these things go away. If you have a massive Hearthstone collection, like someone like me might have had, you don't own that, and you don't get to take it or do anything with it that the company does not want you to do. With a digital ownership based on a secret key, The secret key is the only thing that can transact with that asset. So while someone could like break into my house and like beat me with a wrench to like move my thing, like give us your private key, you still have not compromised the system. There's not a central point to where you can now access the entire thing or move whatever you want. Okay, so those are kind of the properties. Let's look at the tech itself. So we have been talking about Bitcoin, but in a programming context, Bitcoin does have a scripting language, but we need something else to really make it interesting from a developer perspective, and that is a virtual machine that sits on top of this. And so when you add this virtual machine, you get Ethereum. So the EVM is the Ethereum virtual machine. I'm sure you've heard of Ethereum. Started in 2013, went live in 2015. Vitalik Buterin, probably the most notable founder. You've probably heard his name. You've probably seen him online. Insanely smart dude. If we were going to give a description of Ethereum, you could say that it's a general purpose programmable blockchain that can execute arbitrary code. So basically anything you can code, you can put into an Ethereum app and have it interact with this ledger. Okay, next let's look at what this ledger looks like from the Ethereum perspective. You can think of the Ethereum world state almost as an array that is indexed by addresses, and it has an account. And there's two types of accounts. One would be the user account or an externally owned account. It is controlled by a private key, has things like a balance. There's no code attached and there's no storage attached. And to talk about the next type of account are smart contract or contract accounts. Contract accounts have code stored on them and they have storage for that contract. Instead of using a private key, you invoke a function on a smart contract by sending it a message. Okay, let's do a quick recap here. When we think of the internet, I think of this distributed, you've got servers everywhere, we're calling all these APIs, you've got apps talking, it's this widely interconnected thing. Ethereum is similar to that in that you have all these miners, people submitting transactions. But the interesting part is that when it executes, that node executes in a single-threaded local status. So all the contracts, all the data is on that machine. So you're not making an API call to somewhere else. You could be literally one address in memory over is the next contract that you're calling. So all the data is local on the machine, and then that is propagated against the network, which kind of blows my mind that it's this flurry activity, and then it becomes this like singleton state for a moment to do a transaction. It's kind of cool. It has some interesting properties. So we've all heard of wallets. A common misconception is that a wallet holds tokens. A wallet is an application that holds private keys and allows you to interact with the blockchain. So your wallet on your phone or your MetaMask or your Ledger, which is a hardware like cold wallet, there's no tokens in that. It is holding the keys that allow you to move the tokens on the public state, which is stored on every miner. Your balance is stored on the world state of the node. Okay, let's talk about contract execution. So you have all these users, they're submitting transactions to this thing called the mempool, and then miners or nodes in the system are pulling out these transactions and they're running them and they're passing on that state to everyone else. Now, Ethereum can execute arbitrary code. So what stops somebody from doing like this? Which that would slow things down for a while. I didn't mean that to be a pun, but it worked. Or this. What if someone's like store this gigantic video and then propagate it to the entire system forever? It seems kind of bad. So the way that these systems deal with this is they implement this concept called gas. And gas is the cost to pay for whatever you're trying to do, what you're trying to store, the state you're trying to change. So if you write this in a contract, this is compiled into bytecode, which is then compiled into assembly or EVM opcodes. And each one of these opcodes has a gas cost. So the more computation you do, the more expensive the cost is going to be for you. And that helps balance the system to where you're paying appropriately for the work you're causing everyone else to do. Okay, let's talk about dApps. I don't know how to spell dApps. It's like one of those three. So we have our Web2 stuff, our browsers, our servers, React frameworks, and then we have the blockchain. But how do we connect these two things? So the way you do this is through an RPC connection to a node. If you're running an Ethereum node at home, you could connect to that. You could submit transactions through it. You could read from the chain from it. That is like technically the most secure and most Web3 centric way to do it, but not everyone does that. So you have Web2 providers like Alchemy or Infura, who basically give you these nice Web2 APIs to send transactions and to query. And then wallets like MetaMask have this kind of built in the background. So when you install MetaMask, you already know how to send transactions because it has this underlying system in there. Okay, it's time for code. I need my official microphone stand holder, Aaron. Round of applause for Aaron. So here's what we're going to make. We're going to make, I call it bento blocks, which I love that name. It's a dinner marketplace where chefs can create dinners and set a price. A user can reserve a spot, and then the chef can withdraw that money. To do this, we're going to use Hardhat, which is a CLI and tooling for contracts. And then we're going to use some of our old home favorites. We've got React. We've got this thing called Vaporwave Stack, which is something that a startup dev has created as kind of like a Web3 starter kit that's built on Remix. If you don't know what Remix is, go see Ryan's talk from last month. And then we'll use this Ethers.js library, which gives us this nice API to talk to blockchain things. And there's also one called Web3.js, which is about the same. All right. Thank you. Got a mirror. Got to change my display. Let's go mirror with luck. Okay, we're here. I'll bump up the font a little bit. How's that? Readable? More? Okay. On the left here, I have a Solidity file, and I've left myself some notes so we can do this correctly and fast. So I have a contract here. I'm using the keyword contract. I'm calling it bento blocks live. I also have bento blocks the backup in case this goes poorly. And then on the right, I have some tests through Hardhat. Uses similar things like you have used if you've used Mocha or any of those testing frameworks. So I've got some tests here. They're currently failing. So if I npm run test, and we'll see there's a lot of failures here. Okay, so let's start with this create dinner function. And let's make our first smart contract. Okay, so the first test I have over here is that creating a dinner should fail without sending a valid price. There has to be a price per person. If you send something wrong, then we're not going to let you create it. So to do that in this create dinner function, which is taking in a name, it's taking in a price, which is an integer, and it's a public function, so you can call it. So the first thing we're going to say require that the price is greater than 0. This is just a quick guard check to make sure that we have a price here. So I'm going to start with that. I'll just kind of run the test at the end to prove that this is right. If we look at the next one, it creates a new dinner. Now let's kind of look at what we're doing here. So the first thing I do in the test is I call ethers, which is the library, get signers. These are private keys that are already loaded up for me in the test system. And so I'm saying that this is the chef, this account. I'm going to make a price for this dinner. I'm going to connect as the chef on the contract, and then I'm going to call the create dinner function. And then after, I'm going to pull that back out and just kind of assert that the properties are what I think they are. The name worked, the price worked, the balance is 0. Okay, so to create this dinner, first thing I need to do is have something that will store these dinners. And I'm going to use a mapping, which, similar to other languages, if you've heard of maps or dictionaries or hashes, key-value pair. So I have an address as the key, and I'm going to use this dinner struct to store this data. So the data we just saw, name, price, and balance. So to create this dinner, I'm going to say dinners, and then for the key, I want the address of the person that has sent this transaction. This is the chef creating their dinner, and there's a special block variable called message.sender. And so this is the address of the person who sent the transaction. So we're going to do that, and then we're going to create a new dinner here. Say the name is the name, Price is the price. Doing real good on typing. And the balance is 0. And so that stores in the state of this contract a new dinner. The variables you declare up here are the actual storage of the contract. You can see here the name is based in memory. These parameters, an integer by default, is a memory-based thing. So these go away at the end. If I want to store something on the public state of Ethereum, I need these state variables. Solidity is an interesting language. It feels a little bit kind of like a blend between C and JavaScript, because there's some low-level stuff where like I'm using an unsigned 256-bit integer, other than just saying like integer or number. But it has like kind of the similar constructs that you'd maybe see in JavaScript. The next thing I'm going to do here is I'm going to emit an event. So if you think about a transaction running on someone's computer, there's like no console log that you can see or use there. So you can essentially write logs to the state called events that help you figure out what happened. You can listen for those. So I know when a dinner is created, if I wanted to do something, I could listen for that log. So to emit the event, I'm going to create the event up here. I'm going to call it dinner created. I'm going to pass in the chef address, the name and the price. I'm going to say emit dinner created. So we're going to do message.sender is the chef, pass the name, pass the price. It's giving me something here. Aaron's so good. That's why you're up here. Did something wrong here. Missing a semi up here. Okay. So now, if we did that right, we should have this test pass. We did. Aaron, you're doing great. Okay. Now, moving on to reserving. So this is the user. We're going to start by creating a dinner for everybody, because you need that in the system to reserve. And then we're going to assert that this should fail if the dinner doesn't exist. This should fail if you don't pay the correct price. And then finally, it should reserve your spot, create a reservation, admit an event, similar to what we did. So in this reserve function, the first thing we're going to do is we're going to query this dinner. So we say dinner equal dinners. And we passed in the chef address here, and so we're going to look that up again as the key. We're going to require that the dinner.price is greater than 0. And the message I had here was dinner doesn't exist. There's kind of an interesting quirk of Ethereum in that everything is 0 initialized. So you might expect me to have like a null or an undefined value come back. But when I query this address, it gives me back a 0 initialized dinner struct. So I could put an ID here. I could assert that that was not 0. I could do like an isActive for like a Boolean. Basically, like you're going to get an object back. It's just empty and it really is not there. So this is kind of a quirk of Solidity where, in my case, I'm requiring the price to be there, so I can use that to check. But this is one of the things that like trips you up right at the start. There's no null or undefined. There's just 0 state. So integers are 0. Addresses are the 0 address. Bytes are the 0 bytes. Again, kind of this weird mix of low-level and high-level stuff. Okay, so let's require that the payment they sent in is matching the price. So we're going to require that we're going to use a special block variable here, message.value. That's the Ethereum that was sent with this transaction. Is equal to the dinner.price. And if not, we're going to say payment required. Next, we're going to create a reservation. So I'm going to jump up here and uncomment. For the reservations, I have a map from the chef address to an array of addresses. These are the people that will be using doing the dinner. So I'm going to say reservations of the chef. And I'm going to push the sender of this transaction. This is the user that is reserving, and so they are being added to the list of people who are attending. Next, I'm going to add the payment to the balance of the dinner so that the chef can pull that balance back out when it's time to cook or get materials. So we're going to increment the dinner by the value that was passed in. And then finally, I need to get the event. And we're going to emit, reservation made. We say chef. We're going to say message.sender. And then that should work. All right, one more, Aaron, then you're off the hook. Oh, There's a problem. I knew this would happen. Expected 0 to equal 1 with a lot of zeros. Now where this is failing is it's failing on the dinner balance. We're saying that we passed in 0.01 here. We expected to see that when we got it back out. We got 0, but we expected it to be this gigantic number. And this is because in the Ethereum world state, you don't store Ether, you store something called Wei. And 1 Ether, I'll go ahead and type this so it's easier. 1 Ether is equal to 10 to the 18th. Cannot type at all. 0. Wei. I don't really know exactly why this is the case. My guess is that if you think about storing floating point numbers at like a byte level, there's no like half of a bit. There's no such thing as floating point. You store integers, and then your interpretation of the data gives you a floating point number at the like application layer. So my guess is that they're like, people are going to want to send 0.0001 Ether. What if we just stored that as this gigantic number in Wei? Because no one's probably ever going to transact below 1 Wei, because no one's going to send 1 10 to the 18th of Ether. That's just like such an, I don't even know what number that is. Trillion is like 12 decimal places. We're talking like quintillionth of an Ether. So it's just kind of a weird quirk in the system of how everything is done with this like Wei value. And then on the application layer, you have to like convert that. And so you can see when I have the price variable here, where's that? Wrong side. Yeah, so I'm saying ethers.utils parse units. So I'm saying give me in Wei what 0.01 Ether is. So the problem here, and why this test is not passing, is because I'm not actually writing back to the state right now. So I pulled in this dinner variable in memory. So when this variable is changed, at the end of this function, it goes away. And so there's two things I can do here. I can say that I want storage. And so I'm basically getting a reference to the storage, but any change I make will actually write it back. And so that should work. The other way you can do is you can like you can reference it directly. So if I said like this dot balance plus equal, you know, I could actually just reference the state variable. Two different ways to do it. Okay, last one, withdraw. Okay.
Use that left arm.
Okay, this, very good. This one is much easier. Last one, Aaron. You could do this all day. It's Captain America reference. So the dinner should fail if it doesn't exist. Same thing we did. It allows the chef to withdraw only if there's a bounce. So let's retrieve the dinner. This one can just be memory because we're not going to be like, actually no, this needs to be storage because we're going to be updating the balance. So dinner, we're going to use message.sender because the chef is sending this transaction. We're going to require that the dinner.price is greater than 0. And say dinner doesn't exist. Going to require that the dinner.balance is greater than 0. So once you withdraw the money, you can't withdraw more money. And then we're going to say, we're going to call a variable called amount. It's going to be the dinner.balance. We're going to say dinner.balance equals 0. And then we're going to do this kind of weird syntax. And this is how we're actually going to send the Ether to the person. So we're going to say message.sender, call. We're going to pass the value. And then you can pass some extra data here. A little bit weird, but this line is just sending the actual Ether. And if I did that right, everything should work. Cool. Okay, so here's our contract. Now, how do we use this? So if I go into my hard hat directory, what I could do here is I could run npx hardhat deploy. I could pass the network that I want to deploy to. I could do local. I could do a test net. So Rinkeby is one of the test nets, or I could do mainnet. Deploying to mainnet would cost like actual Ether to do that because it costs gas to deploy something. But I've already deployed that. I have this app running. Here's my beautiful app. So what I'm going to do here is I'm going to first connect my wallet. So I have MetaMask over here. I need to connect this account and give the app access to my public key, like account information. I'm not actually doing any transactions. If you don't see gas, you're not writing anything. So a lot of people get scared about like, oh, I'm going to lose all my stuff. If you don't see gas, you cannot write to the well, that's not totally true because you can't do meta transactions. So be very afraid, I guess is my only thing. Okay, so I've connected, it knows who I am, you can see up here. And then let's say we're making a dinner. I had food on the mind when I was doing this talk, so you can see why it's kind of throughout all of it. So create dinner, pops open my MetaMask transaction. You can see that it's trying to estimate my gas fee based on what is happening in the network right now. Gas will go up or down based on how congested it is. So I'm going to confirm this, and then this will now go run, is sent to the mempool, a miner will pick it up, and then propagate that transaction. So I have another browser window that I'm not sure where it went, but let's go to this address, for example. So here I'm looking at a block explorer tool called Etherscan on Rinkeby. If we just look at some of these transactions, you can see all the transactions in the network. Here's the latest block. It was 37 seconds ago. Here's the latest transaction. Here's the transaction hash. It was a success. You can see the contract they called. You can see the gas price they paid. And then if we click on this contract, we can see, this isn't the one that I deployed because my browser went away, but you can see what they're calling. They called mint, they called set approval. And then if you verify the contract, which a lot of people do because would you run some random bytecode string? It's like, probably not. So verify it and it'll actually show the source code so you feel better about, like, I can audit this and see that this is actually the contract that I'm running. So when I call mint, I'm actually running mint and I can go find that function. So if we come back here, that probably had enough time to do its thing. Refresh, we'll see that my dinner was created. For the sake of time, the diner can reserve and the chef can withdraw. The part that I will show you in the React app, if I look at, let's see, like the create dinner component, pretty standard stuff. On click on this create button, I'm calling create dinner. And so I have this file that has basically all my blockchain stuff in it. And so I'm passing in the signer. This is the MetaMask account, the person who has the private key. And to interact with the contract, I've stored what is called the ABI. This is basically a JSON blob that tells the library everything about this contract. It tells me what the functions are, tells me what their types are, it tells me the address. And so to call this, I'm going to say ethers.contract, pass in the address, pass in the ABI and the signer, and then it's like any other function call. So await contract.createDinner, just another API from the front end's perspective. Really nothing exciting going on there. Okay, give a hand for Aaron and his muscles. All right.
That browser tab might be where your Google slideshow is. You have some other times.
Yeah, I was trying to do the like switch tab, but I was not seeing it. Okay. Let me try and get my slides back. Stop mirroring. Did I get my slides? Go internet. Okay. Let's do that again, but let's get closer to the actual part. Okay. Couple more kind of ideas to leave you with, and then I will open it up for questions. Okay. you kind of see how these systems work. Let's talk about some of the criticisms. The one that everyone kind of talks about is energy usage. Bitcoin currently consumes around 0.55% of the global electricity production, similar to Malaysia or Sweden. How much energy should a monetary system consume? This is a big paragraph, but it basically says, if you think that Bitcoin is only for money laundering and Ponzi's, you're not going to think it's worth much. If you use it to escape inflation, monetary repression, capital controls, you might think it's useful. So the value of Bitcoin to you is how much value you think it creates for society. That's kind of your judgment to make. Now, one little caveat here is Ethereum is planning on, it's aimed for September of this year to move to a proof of stake system. So you remove the race to figure out the hash in the proof of work system, and instead you stake some of your coins as collateral, and there's a random process to where if you are a bad actor, they slash your stake. So this removes that churning in that race. If you do things bad, you lose money, so it's a powerful incentive. But Bitcoin has no plans to leave proof of work, and it's kind of integral to their belief of its security. But there are many chains who are already proof of stake right now. Ethereum is just big, and changing a decentralized gigantic system is hard and takes a lot of work. Okay, here's the fun one. Is it a little wild that pictures of monkeys sell for millions of dollars? Yeah, that's kind of wild. I think anyone could agree with that. I think we're missing the point with NFTs. So when you get a new system, people build what they know and what they can do. So people saw this and they're like, yeah, trading and art. I know those things. I can trade and I can do art on this. The part that I think people are missing is NFTs are programmable identity. So this is an example of one of the cooler approaches I found. This is an art NFT, but the creator in the contract, an NFT is just state in a contract. The metadata is stored on that state that points to the images or whatever. He made this thing called the collector, which is this tree image on the left. And in the contract, the owner of the NFT can produce these kind of fractal generational subtrees based on these like entropy factors. And you can only do like 100 of them. It's baked into the code. So deciding when to own this and what to do with it is now kind of an interesting thing because you have control over the shape of this art. I think about programmable identity as maybe plane tickets, maybe access to a location, maybe it is a restaurant ticket. I think we're stuck on this art thing, but like an NFT is code and it can do anything that code can do. It's also unique to its contract. That's one of the properties. So if you think like, what can I do with a unique object that is backed by code? Like that's the frame of mind I think we need to be pursuing. I mean, as long as people are making millions of dollars doing this, people are going to do that. But, you know, there's more. All right, this is a fun one. So there's a lot of hacks and scams and Ponzi's. I will be the first to admit that in the crypto space. It's a new space. People don't know what they're doing. I was looking at one of these and I was like, top hacks of June. Okay, that's bad. There's a lot of hacks. But the thing to remember here is blockchains are hostile environments. So it is compared to this book called The Dark Forest, which I haven't read, so I can't spoil it. But basically, this is a hostile environment where there are bad people trying to do bad things. So in the Web 2 world, we kind of think of this like server database connection as trusted, right? If the server or the database get corrupted or taken over, like we're screwed. But outside of this bubble, things are bad. But in our little like server database connection, like things are good. In the blockchain world, the world state is public. The contract bytecode is public. Transactions are sent to a public mempool. So everything is open and available. This is kind of a conspiratorial question, but I wonder if all of our financial systems were completely open with source code, you could see all their APIs, you could see every transaction. Like, is it reasonable to believe that we would see and know of a lot more hacks? I personally think so, but again, kind of conspiratorial phrasing. So let's look at an example. In our contract, we called withdraw. This is the function we had. And again, these are slide notes and slide code, so please do not put this in a real contract without verifying it. But what happens if you swap these two lines right here? We zeroed out the balance, we sent the ether. What happens if we send the ether and we zero out the balance? Does anyone want to take a guess that's not already seen this problem? The one on the left is okay. The one on the right, you lose all the money in your contract. So this is called reentrancy. This line right here, you think you're sending money to an address. All good. But that address can be a contract, and that can execute code. And there's a generic fallback function on a contract called receive. When a contract receives money and you didn't call a specific function, it runs this code. So that contract can then hit that hook and call back into your contract, where it runs the logic again and gets paid again, and do this over and over and over and over until all the ether in your contract is gone. So one chef could take all the money in the entire contract. And the reason is because we didn't zero out the balance before. So once they've taken all the money, then this line is run where it zeroes out the balance. And so if you look at the right way versus the not right way, because we didn't do it first, when it re-enters, that require does not get hit. Because remember, everything executes in a single thread, and so it will just call these lines one after the other. You can also put a mutex around this. There's other ways to fix this, but this is like a very common hack where people don't realize I gave control of my code to an external contract by calling out to it. And that's like prime danger zone for anything bad happening, because you can't predict what that is. You don't know what's going to come later that might enable another contract to now enable yours to do something bad. I don't think I've mentioned yet, but when you deploy a contract, it is permanent. There are no updates. There's no changing unless you put in code that specifically gives you abilities on that contract. It's out there. So if you deploy a bug, you're kind of in trouble. There are like upgradable contracts, which have their own quirks as well, but most contracts are just deployed and then it can be bad. Nothing is hidden. Just takes one line of code to get the storage. Remember, this is all sitting on the miner's computer. So there's no like storing a password, hope they don't get it, like very easy to get. One last thing I'll show you, which I think it goes pretty deep and it kind of blows my mind, but what happens if miners are malicious in this system, which they are? So you're submitting these transactions and you might say like, hey, I would like to withdraw my money, please. And the miner could say, that's a nice transaction you got there. What if I put my address in there? Or what if I did things before or after what you did, simulate it locally, because I have all the state, I have all the contracts, and let me see what happens. And I can write bots that will do this. A common example of this is a sandwich attack. So miner says, hey, John wants to buy these tokens. I'm going to go get a flash loan, which is basically like a loan you can get from a money market protocol that you have to pay back by the end. Flash loans like mess up a lot of things. But so I want to buy this thing. I'm going to go buy all these things and raise up the price. Then I'm going to run your transaction. And then I'm going to sell and take the profit and give you worse execution. So miners as like a adversarial force put some really interesting kind of dynamics on this. There's also some positive ones as well. And then finally, when we're talking about hacks, the root of all evil, optimization. If I do a for loop, it takes some amount of gas. If I store the length before and just reference it, that saves gas. If I do a prefix plus I, that saves more gas. If I tell the compiler to not check this operation, because I know it's safe, I++, that saves more. And if I do unchecked plus I, that's even more gas. Now, if you have a large project, gas savings could mean like literal tens of thousands or millions of dollars saved, because the user is always paying for that computation. So if your computation is more efficient, they pay less gas. If you've heard of OpenSea, which is like an NFT marketplace platform, they just released a thing called Seaport that has like tons of assembly in it, because you can like tell Solidity, I'm going to drop into assembly here. That makes no sense to me whatsoever. Supposedly this is swapping a token, but yes, this saves a ton of gas because you remove all those nice compiler checks. But tell me that you're not going to mess this up. They're very good and have good engineers, so maybe they can do it. But okay, nearing the end here. Will it succeed? The amount of fees these systems process is gigantic. People are investing in it huge. These systems are huge and able to make changes. Ethereum just did a proposal, was it this year or last year? I think it was early last year, where they changed how their gas and fee structure works. It took like several years of research. If you think about trying to move a decentralized system where you have to coordinate with miners, you have to coordinate with all the clients who are writing wallets and stuff. And so like, It's a pretty big change and it went off pretty much flawlessly. So that's a huge sign of success in my mind. Okay, some not so bold predictions. Where does Web3 go? Maybe everyone and everything has a wallet. That could totally happen. Maybe the blockchain sits behind systems. So we get like verified by Ethereum, like you'd have like fulfilled by Amazon. Maybe it goes the path of AI and ML, where there's like select companies that only do this thing and they're powering, like Google did AI. Now there's like AI for your laundromat business, SaaS, so like things kind of trickle down. In the worst case, I think these cryptography and kind of trust primitives make their way back into Web 2, because that's the really interesting part. Like, why do I have to give you my checking account and my routing account number or my credit card number to buy something? Like, that should be a signed transaction using public-private keys. Okay. What's it like in Web 3? Very high energy culture. If you haven't been in a high energy culture dev environment, it's a lot of fun. People are excited to be building. They're not just trying to flip NFTs and tokens. Bleeding edge tech can be painful. There's some rough edges in the developer experience. And I think, honestly, there's very little downside. Like, the worst case is I go back to doing what I did. The best case is I'm exposed to this new leading branch of technology and it takes hold. And that's great. All right, final slide. How to get into Web3. Lots of examples here. Solidity by example will teach you the syntax, and I'll post these slides on Twitter so you can get them. Crypto Zombies builds like a zombie game using contracts. Build Space is a great site. All this is free. They'll walk you through like making your first NFT, making your first contract. Ethernaut DAO is fun. It's kind of like a hack the box. Like, they put up a bunch of vulnerable contracts, and so you get to try and like break them. Some of those are intense and like I'd spend several days working on, but very satisfying. All right, I know that we don't have a lot of time left, but what questions do you have?